Welcome, girls and ghouls, to a particularly spooktacular evening in the lab. I love Halloween, and I'm throwing a Halloween party, so I want to go all out on the Mad Scientist Laboratory this year. You see, I got a whole bunch of these test tubes here, and I think they'd be really fun to serve drinks in. However, over the course of the evening, I think people are going to want refills. So in comes these separation cylinders. Separation flask? Anyway, my idea is pretty simple. Once you need your refill, you come up and dispense your drink. However, why do this by hand? What if we had some sort of control panel that could be operated by our victim guests of our party? It could be pretty straightforward. You just take your test tube, put it under here, press a button, and have the exact right amount of drink. So, without further ado, let's dive into the realm of robotics, programming, electrical engineering, and spooky action at a distance. Okay, here we have our separating funnel. And it's this valve right here that we need to control. I think our game plan here will be to rotate our funnel like so, and to attach a mechanism right here that will turn our valve off and back on. Now, what can accomplish this? How about one of these? Here we have a pretty run-of-the-mill hobbyist servo motor, and some 3D printed parts to couple this servo to the valve and the stem. Now, I did not design these parts particularly well, so let's make a few modifications. Alrighty, this guy needs a hole drilled in the middle. Yeah, that should do. Alright, we're gonna take our little servo horn here. There we go. We'll attach it in the middle with this small screw. Make sure we get that nice and centered. Yeah, that'll be good enough. We'll go around back. Oh yeah. Now let's remove our separating funnel. Get this clamp out of the way. And our last 3D printed piece is this press fit piece for our servo motor. I'm going to remove this peg from our separation funnel. Let's actually close it first. Then the funnel. Let's actually move this down a little bit. That should slide down. And that should do it for the mechanical coupling. Here I have a little servo test controller.
What is that controlling?
Got it wired up to the servo right now, and if I apply power, I should be able to control the servo manually. While everything seems to work as a dry run, let's try it with a little liquid. Well, that seems to work a treat, which means next, I think it's time to move on to the electrical side of the project. It's trash. Slight little rant here. I went to put together this servo controller and it didn't work. I mean, it should have. I did the bare bones of wiring, just to get one of the servo channels working. But when I went to plug it in, my computer wasn't having any of this. So I tried another one. And another. And another. And now I'm pretty sure I got sold actual garbage on AliExpress. I mean, sorta kinda. This chip right here seems to be an actual Atmel microcontroller. Watch, we can give it power and the light blinks. But it seems like the real problem here is this unlabeled clone of an FTDI chip. It's basically a USB to serial interface. So I guess in the future, if I want to use these, I'm gonna have to replace this clone chip right here with the genuine part. Or I'll just have to wire them up for in-serial programming with another Arduino. But I couldn't be bothered to do that for this project. So I dug out one of my OG Arduino Uno boards. I think this one's a Rev 3 actually, and cobbled together this from a bunch of trash I had lying around. So, how does this thing work? Well, it's actually pretty simple. Its root function is just a breakout for Arduino pins 8 through 13. I've decided I want the Arduino to have 3 button inputs and 3 servo outputs. The buttons will be connected over this 4-pin Molex connector, which is 3 signal lines and a ground line. Basically, shorting any of these 3 pins to ground will indicate a button press. And those button inputs will be on pins 8, 12, and 13. Pins 9, 10, and 11 will be our signal wires for controlling our servos. Now, it's very important that we use pins 9, 10, and 11 on the Arduino, because they're capable of outputting a PWM signal, indicated by these tildes here. By the way, the servos are controlled with a pulse width modulated square wave, where the pulse width correlates to the angle of the servo shaft. Another reason I picked these pins in particular is that they're all right next to each other on the Arduino, except for 5 volts. That's what this random bit of wire here is for. Lastly, I added a little barrel DC jack on the side. This sends direct power to our servos and our Arduino. I didn't read the power spec for the Arduino, but I assume that the servo motors would be drawing quite a bit of current. And this is just a nifty way to power both the Arduino and the motors. All we have to do is plug it into the Arduino starting at pin 8. And of course plugging in our 5-volt wire. Our servo will attach like so, with room for 2 more. And our buttons will plug in here. Simple enough? Next, let's move on to our programming segment. But in order to begin, let's first connect our power and data cables. That up there. Alrighty, I have a blank Arduino sketch open, and we'll start out by including a servo.h library. The great thing about the Arduino IDE for hobbyist electronics projects is that it includes a lot of non-standard C libraries, like the servo library, which saves me a whole bunch of time and allows me to go about the project without writing a servo driver from scratch. And let's create a servo object called drink1. We'll be using this name drink1 to call an instance of the servo library. Let's make an array. Limits 1 with 0 and 180. These are the 2 positions that we'll have our servo go to. Think of it as on and off. All right, now we're into our setup. Weird. And we need to define what pins our servos are on. 1.attach 9. Our servo for dispenser 1 will be on pin 9. And we need a button. Do 8. That will be an input pull-up. Specifying pin 8 as an input pull-up puts effectively a high impedance positive signal on the pin. This way, the pin is always high unless you ground it, ideally through a push button. And now we come to our main loop. We'll start with an if statement. Now reading pin 8 as a digital input by default should result in it being a 1, which is true. Think 1.write limits 1, array position 0. Else, meaning our button has been pressed, array position 1. So in our normal default state, we're going to our limits 1 array, position 0, which is the first position in the array, and writing that to our servo. But if this is to read false, meaning that we've pushed the button, we'll write to servo 1 the second value in our array, which is 180. So yeah, this is pretty bare bones. If you hold down the button, you hold it at 180. If you release it, it should go back to 0. So let's test it out. Okay, this should be button 1. And that works great. However, I don't think these positions are exactly where I want them. Let's change the default to, say, 30 degrees. You know, I bet that's worse. 150? Okay, that's a good default position. 110 for the button close. Not far enough, so let's try 90. 80. 70. 60. I think that works pretty well. Now let's hold the valve open for a little bit. Put a little delay in there. 10. Fun fact, the C++ programming language is a joke. No, really. Take this variable here, I. Well, when we do I++, we're iterating to the next level, inferring that C++ is one step better than C. It's a dumb joke. We'll do a delay 1,000, which is 1,000 milliseconds. So yeah, like a 10-second delay. Of course, we can tweak the delay time further on down the line, but for now, I think this is a good proof of concept. All right, now let's scale our code. We'll get 2 more drinks, keep the limits the same, aside from the naming conventions. 2 and 3 will probably change since it's tailored to each servo motor. All right, we'll attach 2 more servos. Pins 10, 11, and 8, 12, and 13 will be our inputs. You could make a function that handles all of this, but I won't because I'm lazy. Do 8, 12, and 13. Make that drink 2, drink 3, limits 2, and limit 3. And I'll just comment this to make it a little bit easier to read. Ooh, you know what? We should have a global variable that sets the pour time for all the dispensers at once. Dispense rate? Nah. Dispense time. Ooh, but what if the drinks all have different viscosities? Two, 3, 1, 2, 3. All right, I've broken the code. Okay, commenting out just about everything that we had duplicated, fixed it. I see it. Do you see it? I see it. Drink 1 attach 9, drink 1 attach 10, drink 1 attach 11. I just keep reassigning drink 1 to different pins. 2, 3. Okay, now testing servo 1. 2 does nothing. And 3 does nothing. As they should. A little ghost in the machine, I guess. Let's throw another servo at it. Servo 1. Servo 2. Hey. And servo 3. Ah! It works. So, as our last bit of electronics hardware, we'll need some buttons. Now, if these buttons don't say Mad Scientist Laboratory, I don't know what will. Here we have an industrial control panel, which was probably used for some SCADA or process control system. It consists of a Hoffman industrial control panel enclosure with some nice chunky Allen Bradley buttons, plus this nifty emergency stop switch, though I probably won't end up using it. Lifting it up, you can see the button connection terminals on the back, and there's plenty of room inside for fun activities. Personally, I think this makes the perfect place for storing all of our electronics and providing quite the visceral experience for using built-to-last industrial equipment. So let's take it to the bench and get it wired up. First, let's see about getting this Arduino mounted in this enclosure. Okay, now let's wire up our buttons, and that will be these wires here. This actually sucks to do with gloves on. Alright, this top row of terminals is our grounding bus right here. Pin 8. Pin 12. And pin 13. Finally, let's snake our power and servo extension cables through the back. Power right there. This will be for servo number 1, number 2, and number 3. And that should about do it. I think the only thing we have left is the final setup and maybe some troubleshooting. Alright, now this should be pretty close to our final drink dispensing setup. Now, unfortunately, due to an ill-timed Windows update and some negligence on my part of not saving your code, honestly, fitting punishment for forgetting to save, I've taken the liberty to rewrite and optimize some of the code. Most of it is pretty much the same. You can see around here I got rid of the delay variables and got rid of all the if-else statements. Our main loop now begins with these 3 write statements, basically setting our servos to their default positions. This is then followed by these 3 while statements. For example, while our digital read on pin 8 is not high, or low, we write to our drink 1 servo the position that opens up the valve. And as soon as we release the button, which would make this statement not true or false, we exit out of this while loop and fall through to the next 2. If both of these are false as well, we go to the top of the loop and write the close position for all 3 servos. Actually, this might be a little problematic. We do drink 1, drink 2. So as you could see, if I held down drink 1, then drink 2, then release drink 1 would stay open. So we'll just move these statements down under each while loop. We'll upload, and now let's try the same test again. 1, 2, and there we go. Now we can't dispense more than 1 drink at one time. And now the previous valve doesn't get stuck open if we open up the next valve before releasing the previous one. By the way, my wife suggested that we get rid of the time delay altogether and just have it so that when you hold down the button, it keeps the valve open. And I'm inclined to agree with her. Makes it a lot more fun and interactive. Now, testing out the valves, it's clear to see that drink 3 operates correctly. Drink 2 does. But drink 1, well, not so much. That goes back to our limits arrays at the beginning of the code. This position should be the valve closed, and this position should be the valve opened. So let's increase that angle a little bit. And give it another test. That's better, but I think we overshot it a little. There we go. That's much better. Now, time to disconnect it from the computer. And we should be running completely off the power supply now. Let's try valve 1. Huh. This is very strange. What's going on here? Oh God. What's going on this time? Right, let's try resetting the microcontroller. Nope. Stop. Stop doing that, please. Actually, let me see something real quick. Test number 1. See that? Huh? Okay. All right, buddy. Well, it looks like our microcontroller is continuously resetting itself every time it tries to actuate one of the servo motors. My guess is that it's probably too much influx current trying to drive the motors. You see, it was just fine when it was also getting power from the laptop, probably because the Arduino was supplementing any extra current draw from the USB port. Also, given the roughly 10 to 15 feet of really thin power cable I have pushing the 5 volts through, it's no wonder that we have our voltages starting to sag when we activate our motors. Luckily, this should be a pretty quick fix. A 1000 microfarad capacitor should do the trick. We'll solder our negative lead onto our ground and our positive lead onto our 5-volt rail. Well, that would have been bad. Just realized I had the polarity backwards on the capacitor. All right, that should do it. Did not do it. I should probably try getting the capacitor a little bit closer to the chip. Whew, okay. That should do it. Also, good on me for getting the colors completely mismatched. Drink one. Nice. Drink number two. This one seems slower. And drink number three. There we go. Awesome. Now, I think it's finally time we get this set up at the bar. Ghouls, goblins, creatures of the night, prepare yourselves for a terrific fright. Pick your poison and pick it fast. For this fine drink may be your last. Hey, thanks for watching the video. If you enjoy zany mad scientist content, please consider subscribing. In the meantime, take care, and I'll see you in the next one.